our geometry review, so we will do some more stuff as it kind of comes up, but for right now I think we've done enough to where everybody's a little bit reacquainted with these topics. We've warmed back up a little bit. Are you masters? Some of us maybe, a lot of us probably not, but that's okay, right? We remember what SOHCAHTOA is, and we remember kind of how to do some of these things algebraically, and that's kind of enough for right now. As we go and we get into more geometry topics, we'll pause and take some little breathers and reacquaint ourselves with these as it comes up, but I think what we've done so far is probably sufficient. Okay. Today, then, we are going to start chapter 1. So every time we start a chapter, I'll drop in the book pages, the problem set, and then the odd solutions into OneNote. These are all available on My Notre Dame if you click on the textbook link and download and do mess around with all that stuff. But I find it's often easier not to have to be like flipping back and forth through a bunch of windows. If it's all right there for you in the content library, that's pretty nice. The one thing I would ask is when you start doing your homeworks, it's fine to copy the problem page into your OneNote to do the homework, but don't write your answers right next to the problem. Like, write them off to the side, give yourself space to work on problems where there's work to be shown or explanations to be given. Like, please do that. So like, not enough space to like explain something next to these ones or to do some work next to these problems. So just write them on the side, or if you prefer to do your stuff on paper, totally fine. You'll just take a picture of your work and drop it into OneNote, just like we did the picture that you took on the first day. That's fine too. Okay? Everybody's cool with that? And where does the homework go for the homework check? Current homework tab in your section of OneNote. Everybody's cool? What should you remember to do before say I'm done with my homework? Sync your notebook. Everybody remember how to do that? Yes. Okay. Cool. All right. I'm very happy with that. Very good and responsive. Today, starting chapter 1, we did our geometry review. Chapter 1 is largely an Algebra 2 review of topics. So that's what we're going to be doing here for the next several classes. Hello, welcome back. Aiden, it's for you. So the first section from chapter 1 is about functions. Should be relatively familiar with this. That is the overarching topic of all of our Algebra 2 as we talk about what a function is, and then we explore these different types of functions and their properties therein. Sound familiar? Okay. Partially anyways. Again, we'll get more familiar as we review, but again, we would have seen this stuff at some point. Anybody have a decent working definition for a function that they can come up with off the top of their head? Okay. Should be able to do this at this level. This is like the fundamental object of Algebra 1 and Algebra 2 is this idea of a function. Okay. So I'll give you the very technical definition, then we'll walk through some examples of kind of what this means. Okay. So we say that a function from a set D to a set R, so a function is something that kind of connects two sets together, is an assignment, or it's a rule, you could call it, or a map. These are all kind of things you could use interchangeably, such that every element in D is mapped uniquely to an element in R. Now these sets D and R, I chose the letters D and R in this definition for a reason. So this set D, we will commonly call the domain. And this set R, we'll commonly call the range. And those two terms should sound familiar. You should have talked about domains and ranges a fair bit last semester or last year in your Algebra 2 class. So what is this really saying then? It's saying that everything that you have in the domain has to go somewhere in the range, and it can only go, or each thing in the domain only goes to one place in the range. So if I do like f of 5, I can't get 2 answers from that, or 3 answers from that, or 5 answers from that. It just has one answer. Right? That's all we're really saying. Basically, what we want is something that's well defined, so that if I put some one thing in, I always get the same thing back out. Does that feel comfortable? Fairly simple, right? This is verbal or language-wise, that's a complicating sounding definition, but idea-wise, you're just basically talking about a box where you put one thing in, you always get the exact same thing back out, right? If I put a chicken in, I get, a 25-cent coin out. And every time I put a chicken in, I get the exact same coin back out. And if I put in something different, I might get a 25-cent coin back out, or I might get something different out, right? Now, in this case, numbers and coins are or chickens and coins are numbers for us, but, trying to create a metaphor that's easy to understand. So in our Algebra 2 class, we would have talked about some different ways to represent functions, right? One of those different ways to represent functions was with something called a mapping diagram. So a mapping diagram is like a visual representation of our function. So what we're looking at here are the sets D and R that I'm just kind of representing visually. So the 3 dots inside of D would represent the 3 elements that are inside of D. And the 3 dots inside of R would represent the 3 elements contained in set R. So an example of a function might be a map that pairs the first thing in D with the first thing in R, the second thing in D with the second thing in R, the third thing in D with the third thing in R. This is a function because everything in the domain is mapped somewhere, and each of those mappings only goes to one place. Everybody's okay with what we're looking at? Yes. And determining that? So I'm going to draw a couple of other mapping diagrams, and we'll just decide whether these things represent a function or not, and talk about why or why not. Everybody's okay? Okay. And we'll do this for a couple of the other representations also, so that we feel fairly comfortable doing this. All right. Consider this mapping diagram. Does this represent a function? So Nathan says yes. And that is correct. Why doesn't it matter that nothing goes here? Yep, we only care that each domain goes somewhere. Why don't we care that two things are going to that? Because it's a range, right? All we care about is that from each domain, or each thing in the domain, it only goes one place. Could they all go to the same place? Sure, that's fine. As long as you don't have something going to two places. Cool, good. Draw a couple of these. What about this one? Is this a function? No, why not?
Because not all the domains go so.
Great. So we got one of our domains doesn't have a destination, so it's not a function. Excellent. Very good job paying attention. And okay, what about this? Does that represent a function? No, why not? Yeah, so we notice that there is one of our domains is going to two separate places. So that would not represent a function either. Does everybody feel okay if we're looking at a mapping diagram being able to tell? Fairly easy, right? What if instead of a mapping diagram, we had a graph? Right? We can represent a function with a graph. Does this graph represent a function? Yes. Yes is the correct answer. Why? So what you're going to want to think about is every x value has exactly one y value, right? Any x you pick just has one y. Now, when we're given a graph, we don't care so much that every x is used because the domain of the function we draw doesn't have to be all real numbers. Right? So you're just really checking to make sure that x's are used only one time, the ones that are used. Is everybody okay with that? So for example, what I mean is if this was instead a line segment, this is still a function because even though, say, this x value isn't used anywhere, it's still okay. Because the domain will just be the values that are used. You know what I mean? We call that like an implied domain or whatever. So this idea of checking, do you remember there was or checking for a graph, there was a name we gave this test that we just did. Does anybody remember the name that we called this? Yeah, good job, Emma. So we called this a vertical line test. So we're just checking to see if there's any vertical line you can draw that would intersect the function more than once. Now, clearly with this line segment that we have here, no, like any vertical line I draw is going to only hit that thing once. Everybody's okay with that? Okay. right, what if we had instead a circle? Is that a function? No, why not? Yeah, because really easy to see that I can draw a vertical line that's going to intersect that graph twice. What that's saying is the x value here has two different y values. Everybody can see that? Okay. So vertical line test, easy to apply, right? Once we have the graph. What's the trickiest thing you, Mr. Kulik, could possibly do in a situation like this? Well, he could be really sneaky, and he could do something like this. Or that's our function in red, or that's our graph in red, excuse me. Is this a function? There's one vertical line you can draw that's going to intersect twice, but that's it. That's the sneakiest thing Mr. Kulik could do, is just throw an extra point on there somewhere to make it like super close to a function, but just not it. Didn't quite get there. Does everybody kind of see that? Okay. And then the third, probably most common way we've represented functions is with an equation. So let's look at some examples of that. Okay? So let's say we have the equation y equals x squared. Does that represent a function?
No.
So Boyd, you're saying no. Why not?
Like it says, two of the x's go through the y.
Okay. Can you give me an example of? Give me an example of that. So you're saying, like, if I pick x equals 1 and x equals -1, that would give me y is 1 and y is 1, right?
Yeah.
Is that kind of what you're saying?
Yeah.
But that's okay,
It is.
because, well, is it now? That's a great question. Is it?
Yeah, because every x value has a y value.
Okay.
A y value.
But to the
Can I ask? So yes, that is true. Can I ask? You've inferred something there that we haven't stated expressly. How do you know that the x's are representing the domain and the y's are representing the range? That's the convention that we've used. But is it expressly stated here that x needs to be the independent variable and y is the dependent variable? No. So we've assumed that. Is there a way that we could write this so that it was crystal clear that x is the independent variable and y is the dependent variable? Is there a different notation we could have used? The answer is yes. You saw it last year.
Oh, X1.
Not x1. Instead of y, what else could we have started this with? F of x, yes. F of x now is clearly showing us that x is the independent variable because the other variable depends on x. It's f of x.
Are there any bases for y?
If you want it to be. Because here's the thing. X and y are just names, right? Like, if you want y to be the independent variable and x to be the dependent variable, now you're just asking, is x a function in terms of y? And in this case, you'd say no, because we see that y value 1 goes to two different x's. Now, in general, intuitively, we will never do that because we've just, as a mathematics community, decided that x is going to always represent the independent variable and y the dependent variable. But we can take away that ambiguity by using an f of x notation as opposed to a y equals notation. Does that feel okay? Okay, so we've decided here that we said no, we said x is not a function of y based on what Boyd said here. The question, though, remains, is y a function of x? Because that's probably the way that we would naturally want to interpret that. Is everybody okay with where we're at here? So is it easy to do that just by looking at the equation? Well, no, we're not done yet. We just talked about, I wanted to talk about like a notation and why that notation is important, because it imbues this with a lot of more clarity by using f of x as opposed to y, and what the difference is between y equals and f of x equals. Because there's not much, but there's a little bit of specificity there, and we're just expressly stating the independent variable in that case. Because if we assume that y was the independent variable, then this would not represent a function. But that's not usually what we do. We still need to decide whether, if we look at this the usual way, where x is the independent variable, is this a function? What do we think? It's not easy to look at the equation and decide, right? Is there a way we could turn this equation into a different form that might be easier to decide? We could graph it, right? If we knew what the graph looked like, then it would be easy. Everybody agree? What's the easiest way to generate the graph for this? On your calculator. Well, let's do that then.
We should get that website on our.
This calculator emulator, I think I can put the link to it.
Really?
Yeah.
I forgot.
Yeah, remind me. If you send me an email to remind me to do that, I'll see if I can get that to go. I'm not sure you guys will have the install privileges for it, but we can try. And if not, I can ask IT if that's something they can do for us. Anyways, to graph something on your calculator, where do you go? You press the y equals button here in the upper left. And I've got some stuff in here already. I'm going to clear that stuff out. And I'm going to just go ahead and make sure that all of my spots are all emptied out. Because if I haven't used my calculator in a while, it's very easy, if it's been rolling around in my backpack, to end up with some gobbledygook somewhere that's going to throw an error when I try to graph it. So I just scroll to the bottom to make sure that everything is cleared out of there. And then in y1, I'm just going to do y equals x squared. Everybody's all right? Now to graph this, rather than just pressing the graph button, especially because it's been a while since we've graphed anything on our calculator, and I don't know where your guys' windows are going to be at, I would press zoom and then select option 6 called zoom standard. That's going to automatically reset your calculator window to the -10 to +10 in both x and y directions. So what do you guys see here? It's a parabola. Does this pass a vertical line test?
Yes.
Yeah, so is it a function?
Yes.
So we can say, yeah, the graph passes a vertical line test. Great. Was there another way you could have done this? You should have been able to do this just by looking at it. Does this look like something you dealt with last year? Yeah. So this thing looks like it's of the form ax squared plus bx plus c, right? Did you study that last year?
Yeah.
What was that called?
Oh, I know what it is.
No, what is it?
Standard form.
Standard form for a
Right.
what kind of function?
Uh,
Starts with a Q. Quadratic. So this is what our equation, y equals x squared, is a quadratic function. So because it fits the form of something I already know is a function, I know it's a function. I could just have looked at the equation and gone, oh, it's a quadratic function. That's a function. Done. It's okay. Is that okay with you guys? Now, did I expect you guys to go that route? Definitely not. Almost every single time it's like, I would look at the graph. Great. Yes, sir.
I'm still confused about why we turned it into at the beginning.
So
Is it two different problems or is it the same problem?
So what we did in the beginning is we observed that it wasn't clear whether we want to be talking about y as a function of x or x as a function of y, because we get two different answers depending on which one we meant, right? There's nothing about the original problem that states explicitly that x is the independent variable. So if we had assumed y was supposed to be the independent variable, we get that it's not a function. If we assume x is the independent variable, we just saw that it is a function. We can avoid that confusion by using f of x instead of y, because there it is clearly stating to us that x has to be the independent variable because f of x depends on x. Does that clear that up? Is everybody else cool with what we did here? Because we did kind of do two examples inside of one question here, right? So for you guys, if I ask you to do this, I will either state in the directions to like, is y a function of x or x a function of y? I'll state explicitly in the directions, or I'll use the f of x notation. So it'll be very clear as to which one or what to do. Is everybody cool with that? Okay. Again, mathematics, a lot of it is about just like really making sure you say what you mean, right? And so I'm going to try to do a very good job of doing that and talking about why we have to be careful about that. Because if we weren't careful, there's two different answers that you could reasonably answer this with without being specific about what we're really looking for. Okay. So what if we ask, is x cubed plus y squared equal to 1 a function of y in terms of x? So here you notice I added that extra clarifier onto the direction, because can I write this one with an f of x notation? No, right? Because the y has a squared attached to it. So I wanted to be sure I was extra careful to tell you that x is the independent variable. What do you think? What do we want want to try to do to figure this out? Yes.
To get y by itself.
So if you wanted to look at the graph by typing it into your calculator, you would have to rearrange this to get the y by itself. Excellent. Let's try that. Sound good for I think intuitively most of us probably want to start by looking at the graph if we can. Everybody agree?
Yes.
Okay. So to get the y by itself, we would subtract the x cubed from both sides to start. Everybody agree with that? And then what would you want to do next? So we got to get rid of the squared on the y, right? So we'll use a square root. What do you have to remember when you square root both sides of an equation? Plus or minus. Excellent. It was close enough. It was close enough. It's a weird way of saying it, but I knew what he meant, so we just let that one go. Now, what's the problem with trying to type this into your calculator? The plus or minus part. Do we have a plus or minus button on our calculator? No. What can we do, though, instead? Just make it into two equations. Very good. So we can write this as the square root of 1 minus x cubed. And then we can use a second line to make it negative square root 1 minus x cubed. Any questions about the buttons I pressed here? We're all okay? All right. We can just hit graph now since we did Zoom standard last time. The window stays the same. So there's our graph, not a function. Where did my pen go? No. Everybody's okay with that? Yes, Sophia.
Why and what of X?
I'm sorry.
Like, sorry.
Are you talking about this piece right here?
No, sorry. I was asking other questions.
Oh, is y is this equation a function of y in terms of x?
Yeah, I'm good.
If you can't read my penmanship, feel free to ask. I know that it's not always spectacular,
No, you're good.
and being able to read what I say is like, that's an important piece. So if you can't read it, you can ask. It's okay. All right. Was there another way of being able to do this? Considering Mr. Coolidge just drew a line like this, you're going to probably say yes. It's not really. So the other place you could have done, or the other approach you could have taken, is you could have gone and looked for a value for x that could have more than one y that still satisfies this equation. Now, in this case, there's infinitely many of them, but the easiest one, I think, is if x is equal to 0. So if I plug 0 in for x, I get that y squared is equal to 1. And when I square root both sides of that equation, I get two y values, positive 1 and negative 1. So what that's saying is that we have the point 0, 1 and the point 0, negative 1 that satisfy this equation. That can't be a function, right? We have 1x going to 2y's. So if you prefer to do things numerically, that's also a perfectly reasonable way of going about doing that. There's actually an infinite number of these counterexamples for this problem. Now they get a little bit trickier to come up with because you have to use like negative x values, but it'll still work. Does that feel okay? Again, either of these methods is fine. You do not have to do both of the methods ever. In fact, you'd always be able to pick which one you felt like doing. I just wanted to present that there was like a numeric way of approaching this rather than a graphical way. Do we feel okay about deciding whether these things are functions or not? Do we do that like in appropriate detail at a slow enough pace? Okay. Again, I'm getting used to you guys, and you're getting used to me. So I'm going to ask these questions about if we're going too fast or any of these things, especially early on. We're still in like these kind of pseudo review ideas, so I don't want to leave anybody behind during the review in particular, because these are topics that we should remember. And if you don't, we need to kind of clear that up a little bit before we move on. Okay? Our next section is about domains and ranges. But before I talk about domains and ranges, I want to go back and talk about interval notation. This was also something you should have used in your Algebra 2 class. Do you guys remember talking about interval notation? Okay. Do you remember how you used it? Okay, so those are things that you would have used to write interval notations. What did you use interval notation to describe, though? I don't think end behavior. I would have thought domains and ranges, though, because usually you described a domain and range using an interval. So what is an interval notation describing? Describing a set of numbers, right? But more specifically, when we talk about interval notation, we only use interval notation to describe sets of numbers that are continuous. So if you're talking about all the numbers between 2 and 3, that is something we'd use an interval notation to describe. If you're talking about just the numbers 2 and 3, there we'd use like the squiggly set brackets to describe. Is that okay with you guys? So if it's like all the stuff that are between two values or that are bigger than a value or smaller than a value, those are all things that we'd use an interval notation for. If you have gaps in between things, that's something we'd use a regular set to describe. Okay? So what I'm going to do is I'm just going to describe a couple of sets that we can use interval notation to describe, and then we'll talk about how I translate that set in words into an interval. And we'll do a couple examples of that, and then talk about domains and ranges from there on. Sound good? Everybody still okay with the mode? Like, am I doing a good enough explanation of kind of what we're doing and where we're going and what these things are? Okay. So let's just do some examples here. Okay. So let's say we want to talk about the set of real numbers that are less than -5. So I think whenever I'm describing a set or a subset of real numbers like this, I think it's often really helpful to kind of draw the number line to help me represent that. So in this case, I know that -5, I care about that number since it talks about the real numbers less than -5. So when I draw this set now, is -5 a number that's less than -5? No. So I would use a open circle to indicate that that -5 is not included. And then should I be drawing an arrow to the left or to the right? To the left, because those are the numbers that are less than -5 or all live in that direction. So this is describing my interval. So I'm just going to translate this into an interval now. So when I write my interval, it's always of the form like a lower bound. Maybe I'll write that. And then comma, an upper bound. So if I look at that piece that I circled in yellow there, what's the smallest value in that? -infinity. I know -infinity lives down at that left arrow. So that would be my lower bound. The upper bound would be not -6, -5, right? Because that's where that ends. Everybody agree? Now we need to indicate whether the values, the lower bound and the upper bound, are included in that set or not included in that set. So let's start with the -infinity. Is -infinity a number? Not really, right? It's like a concept. If I say, okay, what is -infinity equal to? If you say a number, I can always give you another number smaller than that, right? So can we actually include -infinity in a set? No, right? So the things that are not included, we indicate with a parenthesis. So the infinities, whether -infinity or positive infinity, are always going to get a parenthesis. So is -5 included in our set? No. Why not?
Because it has to be less.
Because we had to be less than -5. We drew it with an open circle to indicate that. So -5 is also going to get a parenthesis. So that is our interval. Let's do another example. Sound good? I think looking at the picture often helps visually, right? Yes, sir. Of course. Yeah. And this is something that I like to do. I think it helps. I'm a picture person. I'm a visual person. If I can see what it is I'm describing, that helps me enormously. Boyd.
So every time there's like an infinity, it's never a bracket. It's a parenthesis.
Correct. Yes. Infinities, whether it's positive infinity or negative infinity, will always get a parenthesis. All right, so our next set is the set of real numbers that are greater than 6, including 6, and less than 10. Since we're talking about the real number line, I'm going to go ahead and draw my real number line. So we got 0, 6, and 10 are the ones that we really kind of care about. I always put 0 in for like a reference, just to remind me where the little things are, or the negatives are. All right. So at 6, that's one of the ones I care about. Do I give that a open circle or a filled in circle? Good. So I use that filled in circle because it's including 6. And then I want the things greater than 6. So which way is my arrow going to be going?
Right.
To the right. Okay. And then my other inequality is less than 10. So at the 10, I'm going to have a open circle or a closed circle? Open. And which way is my arrow going to be going? Left. So really, those two are meeting together. So the word in here that's important to me is this word and. What that word and is implying is it's just the numbers between 6 and 10. Everybody's cool with that?
Yes.
Okay. So let's write our interval. Our lower bound is,
6.
our upper bound is 10. Should 6 get a bracket or a parenthesis? Bracket, because 6 is included in the set, and 10 should get a parenthesis because it's not included in the set. Does everybody feel pretty good so far in what we've done? Okay, let's do one more and then we're going to start talking about domains. All right, so we have the set of real numbers less than or equal to 0 or greater than 4. So we're talking about what happened here. What happened? Oh, there we go. Okay. Since we're talking about real numbers, we'll start with the number line. So we got 0, we got 4. All right, let's start drawing our picture. Less than or equal to 0. So 0 gets a closed circle. And which way is the arrow going to be going? Left. Excellent. And then we have or greater than 4. So 4 gets open and the arrow's going very good. So notice that these arrows are not meeting. The key word here that I'm seeing is the or. This is going to tell me that I'm going to write one interval for this piece and a separate interval for that piece. So far, so good? Okay. Let's start with the left yellow circle. What's the lower bound for that one? Negative infinity. The upper bound is 0. The negative infinity gets a parenthesis. Always a parenthesis for infinities. The 0 gets a bracket. Everybody's good? Okay. Move on to the other one. The lower bound on the other piece is 4. The upper bound is positive infinity. I always put positive. You don't need to write positive, but if I'm doing pluses and minuses, it helps me to remember if I just always put something in front to not forget it for the negatives. You don't need the plus there, though. It's okay if you don't. The 4 gets a parenthesis. The positive infinity gets a parenthesis. And then we need a symbol to go in between them. That is the union symbol. That's that big U with no tail. That means union. That's an operation between two sets that basically says everything in this set and then everything in that other set combined together into one. So that's all the stuff that would be in it. Okay, so this would be our interval. I want to do one more because I thought of one more that comes up that we should talk about. I apologize for lying to you, saying this was the last one. Yes.
We're just talking about the graph.
Yeah, that's okay. Do you have a clarification that you want to ask?
Oh, yeah, we were just wondering why, like, the zero had a bracket.
Great. So if we read this up here, it says less than or equal to. So when we drew that, the 0 got a filled in circle, which means that that 0 should be included in that set. That's why we got a bracket there. But the other one, greater than or equal to 4, that doesn't include 4. So we used the open circle there, which meant it gets a parenthesis down here. Does that help connect those?
Yeah.
Okay. All right. Our last interval notation example, the set of real numbers not equal to 3. Oh boy, Mr. Gulick. What are we going to do with this thing? So what would you propose to draw? I like where your head's at.
Close. All right. I mean, an open circle with arrows going both ways.
Does everybody agree that that is representing everything except for 3?
Yes.
That is correct. Well, we still have to write the interval now. How many intervals do we need? We need 2. We need 1 for this part and then 1 for that part. So we have negative infinity to 3. Good. I heard somebody say that. And what do I use here? Parentheses for both. And then the next interval, u. Okay.
And then 3. Parentheses for both.
Very good. They did say u. That's great. Does everybody feel pretty good about doing this? Is this starting to come back?
Yes.
Good. All right. So let's talk about domains now. We have 2 kinds of domains, and we don't really talk about this much in our Algebra 2 class, but there's really 2 types of domains. There's an implied domain, and then there's a relevant domain. So the implied domain is just your set of numbers possible based on the equation or the equation of the function. A relevant domain is the set of numbers possible based on the equation of the function and the context and now that seems a little vague right now, but I'll give you an example here in a moment where there's some context attached to our equation, and that makes a difference. So here we're given an equation with no context, right? So all we're going to be able to find is a implied domain, which is the easier kind of, or the less we have to worry about, because all we have to do is worry about the equation. So when we're looking for a domain of a function just based on its equation, you want to ask yourself, where is this function undefined? Now, where with the mathematics we've done, there's only two things that have given us an undefined result. Can we think about the two operations or the two things that we can happen where we've gotten undefineds up to this point in our mathematics career?
If you don't know what the y equals x squared.
No, not quite. So let me ask you this. What's 7 divided by 0?
That's undefined.
It's undefined. So dividing by 0 is one of the two situations, right? That gives us an undefined result. What do you get if you solve x squared equals -1? Why? Because you can't square root negatives. Those are the two places that have given us undefined results before. So what we're going to ask ourselves is, can either of those two situations occur? Yes, because we have a square root symbol in here. So what I'm going to care about is just that the stuff under the square root symbol is not negative. So it can be 0 or positive. Everybody's okay with that? So I just need x to be greater than or equal to 4. So if I translate that to a number line, filled in circle at 4 because it's an or equal to, arrow pointing to the right, that would give me the interval 4 to positive infinity. And if we're being specific here, because we're talking about a domain, which variable are we talking about? X's. So we'd write that x is a member of the interval from 4 to positive infinity. And we're done. Not a big deal, right? Boyd.
Okay, how'd you get the first equation again? The x minus 4.
So we observed that there's two places that we can get an undefined result. One of them is dividing by 0, which can't happen in this problem because there's no division. And 2 would be square rooting negatives. We could end up with a square root of a negative in this situation. So what we need to do is we need to take everything underneath the radical and make sure that it's not negative, which would mean it could be greater than or equal to 0. Is that okay? That'll ensure that we don't get something undefined. And if it's not undefined, goes into the domain. So like 5, 7, 12, 168, all those things should be in the domain. And we've covered all of them by taking everything bigger than 4. Is that okay?
What is the symbol after X?
This symbol just means is a member of the set. So in this question, because we're asking for a domain, the domain is about the x's. So to make it clear that we're talking about this interval representing the domain, that's why I put those symbols in front. Does that feel okay? Okay. The next one, a g of x equals 3x over x plus 2. Yes. Yes. All right. Can this function become undefined? Could we square root a negative or divide by 0? Is there, well, there's no square roots in there, so we certainly can't square root a negative. But there is division going on, right? So I need to make sure that the denominator is never 0. Everybody okay with that? So if I solve that, I get that x cannot be negative 2. Ah! This looks just like one of the interval notation problems we did just a moment ago, right? It's almost like Mr. Kulik went, wait a minute. This happens all the time when we do these domain problems. We should cover this interval before we get to the domain part. Everybody recognize that? Yeah. Oops. Any questions on that one? I know I kind of zoomed through that, but it was because it was just like the interval we had done already. Boyd?
So how do we get the 2, 0 for the 2 arrows again?
So we have that x cannot equal negative 2. So it could be the stuff less than negative 2 or the stuff bigger than negative 2. All of that is still going to be things that are not negative 2.
And how do we get the cannot equal with that?
So we know this function, or this would be undefined if we divide by 0. So we know that the denominator then can't be 0. So the x plus 2 was our denominator, and I want that to never be 0. Does that feel good?
Yep.
Okay. All right. Last domain example. All right. So here our last function is v of s is equal to s cubed, but we're given some context attached to this. We're told that v of s represents the volume of a cube, and s would be the side length of that cube. So this is one where we're going to have an implied a relevant domain, because we're given some context to it. So what I want to do first is I want to do the implied domain part first. So if I look at just the equation part, could I square root a negative using this function? No, there's no square roots in it. Could I divide by 0? No, because there's no division in it. So the implied domain would just be everything, all real numbers, right? Since we can't divide by 0 and we can't square a negative with that stuff we have going on there, it just got to be everything. Everybody's okay with that? But if we look at the context now, we're really going to be just worried about this part of the context, because the S is our independent variable. That's the part that's about the domain. So what can I say about the side lengths of a cube? No, what kind of numbers can you have as a side length? All positive real numbers could represent the side length of a cube, right? So we'd say the implied or the relevant domain here would be 0 to positive infinity. Does that feel okay there? Boyd.
So why would it be an minus cap?
Okay. I love those that it's like, wait a minute. And then when you start to say it, it's like, no, I know the answer to this. Makes you feel good as the math teacher. Sophia. Certainly. Kate. Sure.
How did you just get that?
Okay. So if I look at the S cubed piece, is there a square root symbol there?
Yeah.
No. No. So they can't. So there's no square rooting negatives going on. Is there a division symbol going on there? So there can be no divide by negative or divide by 0. So it's everything. So there's no things that could give you undefined, because there's nothing that causes anything to become undefined in the equation. So it's everything. All those numbers are possible, right? Any number I plug in and cube it, I get a number back. There's never going to be a problem doing that. Does that feel okay? Alternatively, if I look at S cubed, that's in the form of a polynomial, right? Does that ring a bell from last year? The domain for every polynomial is always all real numbers. So you could have come up with it that way as well. Been like, oh, it's a polynomial, its domain's all real numbers. Done. Now, would I expect you to have remembered that from last year? No, that's not an expectation that we would have remembered that, but again, we're talking about could have. Okay. You ready to talk about ranges? Actually, we got 5 minutes. That's a bad topic to get into in 5 minutes. This is second tower. Let's do just another example from this, and then we'll say that's good enough, because I don't want to get into ranges right now. That's going to be, I need more than 5 minutes to do that. Nobody's going to be happy with what I've done. So let's just do one more, and this one will be a little bit more difficult. Okay. Thank you. Yeah, so good eye. You should recognize that in this problem you can both divide by 0 and square root negatives. Everybody see that? So from the square root, I can say that x minus 2 has to be greater than or equal to 0. And x minus 5 has to be not equal to 0. Everybody cool with what I observed there? So I have x is greater than 2 and x cannot equal 5. All right, so I'm going to do, since I have 2 of these things going on, I'm going to do 2 colors. I'll do this one in green, and I'll do this in blue. Oops. Everybody's good with what I've drawn here? Now, here's the tricky piece. Because this is an and, what I'm interested in is the overlap in these 2 colors, the overlap between the green and the blue. So that's occurring here and then there. So again, we would need how many intervals to describe this domain? I need 2 because there's a gap at 5. Do you see that? Okay. So I would have the interval from 2 to 5, a bracket on the 2, parenthesis on the 5, union, and then going from 5 to positive infinity. Again, 5 gets a parenthesis, and positive infinity would get a parenthesis. Does that feel okay?
Yes.
Little sneaky there with the break, right? Very easy to miss that. At this point, you guys should be able to do problems up through 10. So 1 through 10. That would be what your problem set for Sunday will consist of. Anything we do on Friday would be go into the week after's problem set. So I want to make sure there's a time in class where you can ask questions about things before I expect things done. Everybody's cool? Where do we turn in Sunday's problem set? Current homework tab on OneNote. You can write it in with your stylus or you can write it by hand and take a picture. Either is okay. 1 through 10. Yes, come on up. And I just...